Good evening, everyone. My name is Dmitry Basov. I'm the chair of the physics department here at UCSD, and it's my distinct honor to welcome everyone to this public lecture on cutting-edge developments in physics. We've started this series of lectures because in my department we really want to share the excitement of physics with the broader San Diego community, and this is the second lecture of its kind, and we couldn't have hoped to have a better partner in this endeavor than Mr. Gary Robbins, who is a science writer for Union Tribune. I don't know how many of you have seen the front page of Union Tribune on Monday. It's all about Oscars and about David Smith. So is Gary here? So he wanted to come, but unfortunately he couldn't make it. So physics is exciting at least two different levels. At the level of at the deeply intellectual level, physics exciting because this science informs us of fundamental laws that govern the world around us. Physics informs us about the origins of universe, and there is a lot of work in this area that's done in my department. In fact, the first inaugural lecture of this series has been given by Professor Brian Keating in my department, who has told the audience about experiments he's doing on early days of universe. He's trying to catch photons that have traveled for 13 billion years before they ended up in his apparatus that he put somewhere in the end of the world. And this was very intriguing. Physics also exciting because fundamental discoveries in physics time and again lead to revolutions in technology and in medicine. Trust me, the laser was not invented by an ophthalmologist who wants to do a LASIK surgery, on you. So, and X-rays were not invented by a physician. And lasers and X-rays and digital cameras and many other household items, these were all discoveries in physics that have led to Nobel Prizes in physics at some time. And the discovery that we will hear today is of that caliber, we believe. David Smith, who is our speaker today, has developed a new transformative technology working here at UCSD in the group of Shelley Schultz. Shelley Schultz is, of course, one of the founding faculty of this university and one of founding faculty of this department, and we are delighted to see him here in the audience. And a round of applause, please, for Shelley. Shelley, we in my department, and I think everyone in this room, we all wish you well. So this technology that David will tell us about is a technology of metamaterials, and he has done groundbreaking experiments here, working in this topic at UCSD. Experiments that one day may enable invisibility of various objects. So this is very important and exciting development. David is from San Diego. He has done his most of his schooling in San Diego. Then he was an undergraduate here in San Diego. Then he was a graduate student with Shelley Schultz in San Diego. He was a research scientist, and it was here at UCSD physics department where he has performed first experiments that we will hear today about. In In 2004, David has moved to Duke University, where he holds an endowed chair position. But he also keeps strong ties to San Diego, and in fact his cell phone number still starts with 619. David is very serious about making the technology that he has invented useful for everyone. And about a year ago, he has started a company in Seattle that will commercialize some of these wonderful inventions. And in fact, many of us already know what these inventions are, but we've learned that from science fiction books. And David is going to make this a reality. Not surprisingly, Bill Gates is one of his investors. And for the work that David has already done, he has received numerous prizes, including the Descartes Prize and an American Physical Society Prize. Certainly many of us are convinced that the work that he has done here, starting with research in Shelley Schultz's lab, is of Nobel caliber. We are excited to follow these developments, and we are thrilled that David has accepted our invitation to speak today. Before I shut up, I would like to thank alumni, UCSD alumni and physics department alumni, and our donors and friends of physics for their generous contributions that allow us to do many things in the department, including having this series of lectures, for example. Those of you who have contributed to the physics department, you know who you are, and I would like to thank you for that. Those who have not contributed to physics department, I know who you are, and I hope you will consider doing this in the future. Please feel free to talk to me after this lecture. We can arrange for your private visit to the department, or I can wash your car if you wish. That's part of my job description. And you should know that your contributions, small or big, are making a big difference in student experience here, or sometimes they boost our research and help help us to train ingenious physicists like David Smith and allow them to fulfill all their dreams and aspirations. And without further ado, Professor David Smith.
Great. So I've never given a talk like this, and the reason I'm giving a talk like this, which is going to be mostly non-technical, is because of this article that appeared in the Union that was heavily slanted towards science fiction and sort of a broader interest type thing. So I want to thank Dmitry and the rest of the department for challenging me to do this. And we'll give it a shot. So I've reordered things. What I work on is something called Metamaterials, and it makes perfect sense to me, but people that aren't specialists, and we work with a lot of media, we talk with a lot of people in the media, and they, when I start talking about metamaterials, they say, whoa, just, what are you actually doing? What is it good for? So I've reordered things in a way that is not how we came about it, but just maybe something to give some motivation and inspiration as to where things might be headed. And certainly these things inspire us, but we don't talk about them that much because it often leads to a little bit of backlash from our colleagues, and because sometimes program managers don't like it. But the reality is, things in science fiction and fantasy often do inspire us and keep us moving towards making contributions in science. So for this talk, I thought that I would take a little bit of a different tact and talk about things as they relate to the world of science fiction. So before I go crazy and start rolling, and I tend to go fast, I know, none of this work happens in a vacuum. There's a lot of collaborators, and there's a lot more than what you see here. And in fact, only some of these people are currently in our group. Some of them have graduated. So like just about everything I'm going to say in this talk, this slide is only about half true. but you will see contributions from all these people and many more that aren't even listed there. I should mention Sir John Pendry, who, at least on this cloaking and invisibility side, has been a great contributor and collaborator, and certainly someone that's been spearheading this field. So I'm going to pick up on what the San Diego Union started with. And this thing's just killing me here, so let me see if I can move this around. What is science fiction? And I've got a list of things here, and I'm not an expert, I'm not a literature expert, but I've read a lot of science fiction. I like it because sci-fi lets you explore technologies that don't exist, and good science fiction explores the impact of those non-existent technologies on humanity. So a good science fiction book will give you a technology that is tied to science, maybe something that it might not be necessarily practical, but it's something that is rooted in science fact, but then they will take off with it and explore its impact. A good sci-fi technology will have both strengths and weaknesses, and actually becomes one of the characters in the story. So a good science fiction story to me will have a technology that's somewhat viable. You can say, yes, I could imagine that would happen, and it is like one of the characters. And through those stories, we can gain a great deal of inspiration, and some of those things actually turn into science fact. So the question that the San Diego Union asked me, did I read science fiction? Was I impacted by that? The answer is definitely yes. And it's very pervasive. I found this, which I thought was just fascinating because, there's good science fiction and there's cartoons, but the Jetsons, I have to say, definitely shaped my vision of the future. I'm not embarrassed about that. But if you look through the Jetsons, and this was done in the 60s, I actually found this. I didn't make this up. The source was some website called designtrending.com. And they picked out some things in the Jetsons that are actually here today. So flat screen TVs, if you don't think about it, they had them on the Jetsons back in the days when a TV was had a tube this big. Video chat was pretty common. Text displays, robot vacuums, we have those now. And if you look in the upper right, you can see a bunch of people standing in line looking at their mobile devices. And we definitely have those. In fact, we've actually one-upped them because ours are a lot smaller than theirs are. And you also notice that what's sort of hidden there is that they've got wireless in the Jetsons, and they definitely did not have that in the 60s. But you can see everything's got an antenna on it. Everything's communicating with everything. So it's just really, you cannot help but have been influenced by watching that and always wishing that the future would come sooner, and it did, except we don't have flying cars just yet. And we're definitely all waiting for that. So, science fiction is important, at least as something that can provide inspiration. And invisibility is definitely a very common science fiction theme. So what I'm going to ask for is a laser pointer. Does anyone have a laser pointer? That, as Dimitri said, is the reason the laser was invented. This works. Okay, great. So it's a long-time concept in science fiction and fantasy, and so I want to start the talk off today saying, before I say what I actually do and have you sit through that, what I want to say is, let's start off from how would we make an invisibility cloak? What are the prospects in terms of science fact for invisibility? And there's a couple methods that I'll talk about. One is that you could match the index of refraction, and I'll tell you what that is, of an object to air. That's one way of doing it. Another way is to route light around an object. So those are a couple ways you can think of achieving invisibility. And you can see this obviously in print and stories, but in the media, all of these, there's lots of examples of the two different methods. The invisible man might be the first method where he's somehow made himself matched to air. Stories like this is Invisible Girl, or Star Trek, which I'll talk more about. Actually, if you read their basis, They are finding a way to route light around some object, and that is a different approach. Of course, there's magic like Harry Potter and Lord of the Rings. And then there's, again, another type of invisibility, which is similar to this, Invisible Man. This is Hollow Man with Kevin Bacon. And illustrated, they're trying to show someone invisible, but underwater, you can kind of see that he's maybe not exactly visible. And then one of my favorite movies ever, Predator, which, because I think presented a very realistic portrayal of invisibility. Not realistic today, but something that you can imagine, even with the technology we're working on, we might be able to imagine happening one day. And so I really like that movie. It's I always like to say it's the really one of the greatest science fiction movies ever. And if you're not a fan of Arnold Schwarzenegger, then I'll say it's one of the greatest Arnold Schwarzenegger movies of all time. And then this is Wonder Woman. I just threw that in there. I can't believe I watched that when I was a kid. So, how do you make something invisible? Well, first you want to ask how we see things in the first place. So if light passes through empty space, what light does is it travels in a line. That's what it does. You can't do anything else to it. It's going to travel in a line. So if there's nothing blocking it, this is what it does. And if you want to make something invisible, you want to make light do or look like it had done exactly this. So the reason that that doesn't happen all the time is if you put an object in the way of light, it reflects. And when it reflects, it means that you send light backwards. So if you're standing here, you can see the light coming back towards you from this object. And if you're standing here, you see a shadow. So there's two ways that you can see or perceive the existence of an object. And even if it's not completely reflective, even if it's something like this, which might be partially like glass, partially transparent, there's an index of refraction difference. There's light still interacts with this somehow. It bends at the interfaces, and so you can see a distortion. So if you look back at poor Kevin Bacon here, that might be something that's happening to him. He's transparent, but he's got enough of a little bit of an index mismatch, and you're actually able to pick him out. So if you want to make something invisible, the best way would be to have light not interact with it at all. And so you have to avoid it, and this might be a picture of how you might want to make something invisible. And then you say, how on earth am I going to do that? That's like water running around a rock in a stream. And you say, that's not going to happen. That's truly science fiction. So back to science fiction. Well, before we go to science fiction, it's actually, you can get a hint from magicians, because magicians have been doing this for a long time. You can use mirrors, and mirrors are actually pretty effective. If you look at some of the work by Chris Angel and some of the others, well, they don't like to even let you think they're using mirrors, but they're using mirrors. And you can imagine that you can route light around, for example, an object like this. It's a long time sort of trick. Here's an example of how you might use mirrors to make someone appear to be headless. And here's a picture I grabbed from the internet showing that how this illusion works. So magicians have been ahead of us on trying to make things invisible. But the downside of this is that it only works for certain angles. And there's often a lot of distortion and problems with this, so that magicians will also throw in some smoke to misdirect you a bit and make it a little bit harder for you to perceive what's going on. So that's why magicians are always talked about as using smoke and mirrors. But it is one way of doing it. It's just not what you would think of to make a cloak. It wouldn't be very useful, for example, if you were in a combat scenario. You're not going to carry a bunch of mirrors around with you, I don't think. So I remembered this episode. We talked about how much we're influenced by science fiction, and there was this entire episode based on an invisibility cloak called Balance of Terror in the original series of Star Trek. And it's an entire story that centers on the strengths and weaknesses of this Romulan cloaking technology. And I wanted to actually play you a little bit of this episode because it's very interesting, actually, how concerned Gene Roddenberry was about getting the science semi-right. So before I tell you, or I show you the clip, actually there are physicists who take these things seriously, and Lawrence Krauss is a physicist who wrote a book called The Physics of Star Trek, which is a really good book. And we talked about how you might route light around something, and that light really wants to travel in a straight line. But it turns out, thanks to Einstein and general relativity, that there's at least a conceptual approach to changing the way light travels by actually warping space itself. So what Einstein demonstrated or postulated was that space could actually be bent if you're near a large mass or a lot of energy. So there's something called gravitational lensing and all sorts of things that many of the people in this room know a lot better than I do. But you can actually curve the trajectory of light around an object and do many things like create warp drives and deflector shields and all sorts of tractor beams, all sorts of things that are done in Star Trek. In fact, Einstein was really science fiction's best friend, I think, because of all the implications associated with general relativity and warping space-time. It gets us around a lot of things like you can't travel faster than the speed of light. Well, if you have enough energy, maybe you can. And this is a way to create an invisibility cloak. Not a practical way, but enough for science fiction. Well, if you're inclined towards science and you're a kid, that's actually a very fascinating episode, and it's actually based in fact. So there's a lot of things that actually make sense here. One, it's not an accident that he said it takes a lot of energy, or hypothesized that it would, because it really would. And if you read Larry Krauss's book, it would take currently a ridiculous amount of energy. So it's not really practical, but who knows in the 23rd, 24th, 25th century. He mentions selective bending of light because that's how this thing would operate. It bends light around itself by actually warping space. Note that the ship becomes visible to other sensors, which is interesting. The ship needs to become visible to engage weapons, and that's a lot of the discussions that we had when we first started talking about invisibility cloaks. Could you see out if you're inside one? The answer is no, and actually it's in this episode. So that is interesting, and I'll just emphasize it takes lots of energy. So it's not very practical, but it stimulates you and makes you think. So is there a more realistic path to invisibility? It's unlikely to curve space, and if you did curve space, by that method you're also curving space-time, so you're changing all the physics, and really lots of crazy things might happen, which again, science fiction authors have thought of and have pursued in various contexts. What's more likely is that maybe you could make a material that would bend rays just like we want to have happen. So is it possible? And the question is, how do we create a material for a cloak that would function the way that, or in some analogous manner? So I'm going to leave it there, and I'm going to talk about what we actually do, because it turns out we don't think about invisibility cloaks all day. We do something called metamaterials, and now I want to take you, drop the invisibility for a second and talk about things that you see, which are materials, what we do, and then come back and show you how those materials can be used for invisibility. So here are materials, lots of materials, you're very familiar with them. They have lots of properties. You're always familiar with the properties. Metals are shiny, they're heavy. They have particular thermal and electromagnetic and optical and all sorts of properties, flexural, things that help you identify when something is a material. If you take a material and you break it into a couple pieces, you've got two pieces of that material. You don't have two things that are different. So materials have intrinsic properties, material properties, and the advantage of thinking about materials is that you can use their properties to engineer things and in different ways, and they're very easy once you have these bulk properties, and that's what physicists like to use. We like to use the simplest equation possible and use the simplest property of the material. So we know what real materials are. We've known for a long time that they're composed of atoms or molecules, and you put these atoms or molecules together, and that gives rise to the properties you see for this macroscopic piece of material. So you don't have to think about something like this piece of wood or the metal is composed of atoms all the time. You just say, I've got a piece of wood, I can do whatever I want to it to shape it into something. But somewhere in the back of your mind, you know it's actually made of a bunch of molecules. There is a connection between the properties of these molecules and atoms and the eventual macroscopic properties of the material that's formed from these atoms and molecules. And that process of going from a discrete bunch of atoms to a material is called homogenization, and physicists have spent a lot of time trying to figure out how you get these properties into something like this. I won't go into all the details, but that's basically the process that we want for metamaterials. So a couple of more technical slides. There are two flavors of interaction that materials have if we're talking about optics or electromagnetics. When we say electromagnetics, immediately we're talking about a field that has an electric component and a magnetic component. And if you look at the atomic level, atoms or molecules interact in a very simple way. It can be written down with a couple of force equations. Basically, an electric field will cause a separation between positive and negative charges, so that you get that interaction. A magnetic field will cause currents to circulate. It's a simplification of what actually happens, but if you keep in mind how these two mechanisms work, a magnetic field gives rise to circulating currents, and an electric field gives rise to a charge polarization, plus and minus charge. That's the basics of interaction, light-matter interaction. That's really all you need to know. So you take these things, which are, we'll call them dipoles, electric or magnetic dipoles, put them together into a material. Maybe there's other interactions that hold the things together, but the electromagnetic response causes a polarization that looks like this, and you've created a material, and you can at least conceptually replace what you see here with something that you can imagine to be continuous. Every material is composed of atoms, but engineers don't think of things at the atomic layer. They think of things that look like this, knowing that in actuality behind it there is this going on. And to describe all this, you don't need all the interactions between all the atoms and molecules. You can lump everything into a couple parameters, and these are often very mysterious to people that haven't thought of E&M, constantly for years and years. These parameters called epsilon and mu, permittivity and permeability. So if you have a material, its basic properties, its basic electromagnetic properties are embodied in these two parameters, and that's what we care about. We need to know, if we're specialists, how to go from this to this, but we can do that. And we can hand this to an engineer, say an engineer trying to make an invisibility cloak, who comes to us and says, I need this epsilon and mu, and we can got that. We know how to do that. So I'll write down this one equation, which is Maxwell's equations, and just show you that Maxwell's equations are the fundamental equations that relate electric fields to each other, and epsilon and mu enter these equations in a certain way that allow us to solve problems of light interacting with materials, and this is how we do it. And just for those that aren't immersed in this, again, this is what an electromagnetic field looks like. It's got an electric component, a magnetic component. This is called a plane wave. A lot of what I'm going to be doing is going to be visualizing these types of waves. So there's a couple ways to do it. This is a plane wave if we look in perspective. And if we look on the side, we see this kind of squiggly sinusoidal thing that we all know, or a lot of us know that's a representation of a wave. We're actually looking at it on the side and just looking at the electric field, for example. And if we look on the top, which is something that we can actually do experimentally, this is what that wave might look like. And we're looking at the peaks and troughs, which are the red and the blue. So the peaks and the troughs. And that's what you see there, and these are called phase fronts. So that's a wave, and that's really all we need, at least for now, for what a wave is. And light is part of that spectrum. So I found this from a site from NASA. I wish it weren't quite so blurry, but what it shows is that the electromagnetic spectrum is gigantic. It stretches from radio waves all the way to X-rays and beyond X-rays to gamma rays and everything else. In between are all electromagnetic waves, and to a physicist, everything here is the same. To a technologist, everything here is different because the technology that manages microwaves versus radio waves versus infrared versus optical, all of those technologies are different, but the physics is all the same. So once you understand the physics of materials or metamaterials, you can really address any part of the electromagnetic spectrum, which is why actually this concept has caught on so well. And I also want to point out that when we talk about invisibility cloaks and we talk about the work we do, which is at microwave, all the reporters and media people say, yeah, but we don't see microwaves. In fact, we only see a sliver of the electromagnetic spectrum. That's what our eyes are sensitive to. But really, there's a lot more there. and lots of devices see down in these wavelengths or up in these wavelengths, and there are tons and tons of examples. You just have to look around a bit. And here's some. So this is reality. This is, for example, night vision goggles, which we'll see in the IR bands, which we don't see, but there are devices that see. This is the L3 ProVision, sorry, I have the name wrong there. ProVision, which sees images at 26.5 gigahertz, that's in the microwave. There's lots of other examples. Obviously, you can take X-rays and see things and create images. So there's plenty of things being visualized across the spectrum. We only see a small sliver of it. And interestingly enough, there's a character in the next generation of Star Trek that has a visor that allows this character to see everything in the spectrum. And from, I think, X-ray or even gamma ray down to RF. And this is just not such a far out concept. This is something that could actually one day be a reality. So there are lots of other ways to see. It's not just all about visible. So also a question that comes up is, what about stealth? And I just thought I'd mention that here. Stealth is not invisibility either. One of the ways that radar has traditionally worked is to send out a signal and look for the return. So what stealth technologies do is either absorb or redirect light that comes at them from, say, a radar system. If you have what's called a multi-static radar system, then nothing's invisible at all, even stealth fighters. In fact, most modern countries now have multi-static radar systems. So this, which is a stealth plane, is, first off, it's clearly not invisible to visible light. And second, it's not even invisible to most modern radar systems anymore. So just a point to make that it's an approach to reducing something's observability, but it's not the kind of invisibility that we're talking about or trying to get. So now when we talk about electromagnetic response, we start with Maxwell's equations, and we've hopefully I've convinced you that everything is sitting in this epsilon and mu. So I'm not the first to do this, but we can imagine creating a couple of axes and putting epsilon and mu to indicate these axes. And this is our parameter space of materials. And then we can look around and see what we actually have to work with. And just to point out that where epsilon is less than 0, you end up with an opaque material. Where mu is less than 0, you end up with an opaque material. And most materials actually sit up in here. And most properties of materials have actually been leveraged up in here. And again, from a physicist's point of view, I'm really oversimplifying everything drastically, but I think that makes sense here. And there's a couple of parameters that we're really interested in. The index of refraction, and again, I'll say what that is, but mathematically, it's just the square root of this parameter times this parameter, the square root of epsilon times mu. There's a couple other things. We have actually what would seem like a very, very large range of material parameters to work with. Epsilon big, epsilon negative, mu big, mu negative. It's not true. Nature doesn't give us everything. In fact, it never gave us this quadrant here at all. There are no materials that have this property. And in fact, a lot of materials that have these properties only occur at certain wavelengths. So it's actually a very limited palette of material response that nature gives us. So we haven't quite filled all this in with naturally occurring materials. So now, what are metamaterials? Metamaterials are taking this concept of atoms or molecules, but instead of atoms or molecules, we duplicate that response with little circuits that look like this. So we can make, for example, an electric response with a little I-beam like that, or a magnetic response with like a little split ring resonator, which is what we call them, where we can cause light to currents to run around in a circle. So we can make artificial response, and nature doesn't know the difference if the wavelength is much larger than these. Nature doesn't know the difference between this and an atom. So using this, we can make materials and put things together that look like this, lots of little circuits, and they have properties. And what you can see is this mu, even if you don't understand what the mu and epsilon are, you can see that you can get basically anything you want, and you can change, I said frequency here, or wavelength, I could have said wavelength. You can put this anywhere by just changing the geometry. So the point is that we now have a whole grab bag of tricks to play to create materials where either it was impossible to get them before, or at least very difficult. And we can, with more and more, we can do this with pinpoint accuracy. So we can really make things that nature didn't imagine, for example. So just to remind you what an index of refraction is, most materials are not matched to free space or vacuum or air. They actually have a little bit of response, and that little bit of response is usually described by the index of refraction. And it's pretty well known that when light comes in at an interface between two materials that have a different index of refraction, that light will bend. And this is, for example, the mechanism behind eyeglasses and many other optical devices, lenses. So this is a ray trace, but showing you what would happen if you shine a laser onto a piece of glass or plastic. You get this bending, and then everyone's usually familiar with this phenomena of, say, a straw in a glass of water, that you see a bending of that, and that's all due to the index of refraction. So the index of refraction is a fundamental property of the material, and it's related to both the electric and magnetic properties of the material. So we talked about the invisible man. I pulled this from the internet. Obviously, there's some things, if you're in water, it's actually easier to do this, and there's a lot of sea monsters, like this jellyfish, that really are mostly clear. These are a bunch of fish swimming around this jellyfish. But you can actually show this effect. So here's a glass rod you might think it's water, but it's actually a couple of oils mixed together to match the index, refractive index of this rod, and you can see it appears to vanish. So that's index matching. And if you think back to Kevin Bacon just a little while ago swimming in the water, and just imagine he was a little bit better matched, you could actually make someone invisible. The problem is we are based on molecules and chemicals and things that aren't going to vanish, so we can't become glass rods. If we could vanish in oil. But that's the invisible man effect. And it really wouldn't be possible to do in air for reasons that I'll talk about. So this is a little bit technical, but I mentioned that if a material has a negative epsilon or mu, it's opaque. And there's a simple experiment you can do. You can just shine light on a material, and if you want to prove that it has for example, mu less than 0, negative, you can look to see how much light gets transmitted, and this is just a transmission curve, and when mu is less than 0, you can see that you get no transmission. It becomes opaque. And this is the kind of experiment we do at microwaves. You could do it at optics, but for various reasons, which I'll talk about in a second, we want to do it at microwaves. And this is work that was done in Shelley Schultz's lab back in UCSD. That we started this round of research back in, I'd say, 97 or 98 is when we really started these concepts. So what I'll show in the next few slides all happened at UCSD. So at that time, we were interested in proving that this structure actually had a negative mu. That was our goal. To make a long story short, a simple way of doing it was to add a negative epsilon to it. And then if you think back to what the refractive index is, it's epsilon times mu. Negative times negative is a positive. So where either of these things were opaque before, either of these materials, if you combine them together, all of a sudden they should become transparent. Not quite transparent, but at least transmissive. So put this together with this, and here's a picture of what we built in 2000 and what we should have expected to get. And I won't go into all the details of this, but basically where it was opaque, it suddenly becomes transmissive. That's the nature of the proof. It turned out that structure has a negative epsilon and a negative mu is something that didn't exist in nature, and we're only dimly aware that that was initially that was important. But after Physical Review Letters rejected our paper on this, I went back and did a literature search and found this paper from 1968 called The Electrodynamics of Substances with Simultaneously Negative Values of Epsilon and Mu, written by this man, Victor Veselago. And really, it was just amazing because Victor Veselago predicted tons and tons of interesting physics that should emerge from such a material, but noted that such a material didn't exist. And in fact, one of the things he predicted is the refractive index could actually be negative. And there is no such material that has this property. And actually, it's pretty wild. There's a lot of interesting physics that comes from this, and I won't go through all of it, but it's very, very stimulating and exciting to think about. So, of course, once we knew what we had, we rewrote the abstract and the introduction, and then PhysRev Letters accepted it. And really, almost instantly, the community got extremely excited about it, and lots of people started working on it. So over the years, here's lots of different types of materials, negative index materials we've made. And the point is, not to make a talk on negative index, but that we can, with artificial materials, this proved you could do something really interesting, something that brings something to the world that didn't exist before. And in fact, if we are correct about it, we should have a refraction diagram where instead of light going on this side, it goes on this side. And there's a lot of fantastic physics. This actually cube was built by Boeing, and it doesn't do anything, but it costs a lot. So I'm going to show you some experiments now, and again, I want to just kind of show you that different ways of visualizing a wave. This is a 1D wave. Waves propagate, so the phase, as you can see, goes in the direction usually where the energy is going, but that's not always the case, especially for negative index materials. And if you look at the side, you can visualize it that way, or what you want to remember is that you're actually looking at a wave front, so this is what you're actually looking at. And if you were to look from the top, which is something we can do experimentally, you can see you get a diagram like that, and you can see that the waves propagate. And so this is our wave. We're not visualizing the magnetic part, but it's there. We're just looking at the electric part. And the electric part in the crests and valleys. So, okay, stop. There we go. So this was the experiment we did that proved negative index. And you can plop this into a numerical simulator. And this is what a wedge would do with positive refraction. Here's a wedge that does negative refraction. You can see that it bends the way you'd expect. And I won't go through this. This was an experiment that was done. Anyway, this is a chamber. We didn't have this at UCSD. This one's at Duke, but we had something very similar. I'm going to show you some data that we took at Duke, just to illustrate it because it's kind of neat. You can put something in here. You can put an antenna in the top, and then you can actually map the field. So you can see something that's invisible. You can see microwaves by this method. We move this plate along, and just like pixel by pixel, we create an image and see what the microwaves are doing. And it's an important way of visualizing things. So here is a simulation of a wave coming in and then refracting at the surface of a piece of Teflon or Rexolite or some kind of plastic. Here's the experiment, and you get pretty good agreement between the two. There's some turbulence caused by things bouncing around, but otherwise you see that you're getting positive refraction. Now, if you make a negative index material, which we can do, what you see is these phase fronts run backwards, and that's really interesting. There's no natural material that will do that. That's a simulation. This is an experiment on that material I showed you before with these rings and these wires, something that doesn't exist. We put it together, and remember, we're treating these things as little atoms, and you put them all together, and you end up with something where you satisfy Veselago's prediction that waves run backwards, and that you get negative refraction, that the light comes out on the other side of the normal. So this is nature of a proof. We did this at UCSD, not these particular experiments, but similar ones, and we thought we'd iron things out. Turned out, oh, and then if you look at actually, if you can do ray tracing to see, gee, what would that look like optically? Well, here's an example of a ray trace that shows that. And if you were to put like a straw in negative index water, you'd see it bending the opposite way. And there's lots of interesting optics associated with that. This is from a group in Germany that did these nice ray traces. Anyway, it turned out to be very controversial for a while. And we had papers like this. Initially, they were called left-handed materials, not negative index. And we had papers like this saying left-handed materials do not make a perfect lens. I won't even go into what that is. Problem of left-handed materials. Lots of papers coming out, even by experts. Is there an experimental verification of a negative index of refraction yet? And I think I actually reviewed this paper. And the original title was, is there an experimental verification of a negative index of refraction yet? No. And so at least I got them to remove the no. Really, some of these guys were very good people, and they were very confused by the possibility of negative index. Wave refraction and negative index media, always positive and very inhomogeneous. Paper causes a lot of trouble. And then it was carried out in the popular science media, lots of different things. Left-handed material reacts to 3D light, heat and light. Does negative refraction really exist? Good and bad. There's some other here. Oh, I think on the next piece, we have lots of interesting things. Negative reaction to negative refraction, very cute. Theorists doubt claims for perfect lens, all this sort of stuff. But in the end, time was on our side, and we were able to write this. Sir John Pendry wrote this final statement, positively negative. So if you're worried, don't worry. It's all grounded in fact, and it works. It's not science fiction. So that is a lot of introduction to what we do. We can make artificial materials, and we've proved, I'll just state that we've proved that we can do things that nature did not provide. We can make really designer properties, just dial in what you want, and we can make it. So now I want to return to the topic, does any of this help us to make an invisibility cloak? So there is an effect that's well known. It's called the Mirage, which is something that should give us some hope. So I've talked about things that just have a constant index of refraction. But if you imagine grading the index, you can actually cause light to move through a medium that has a graded index like this. So whereas light would do this normally, if you grade the index and make it inhomogeneous, make it vary, in fact, with this function here, you can actually cause it to curve. And if you look down the road on a hot day, you see what looks like water on the road, and that's the mirage effect. What you're actually seeing is the sky, and there's air above the road. The road heats the air up and creates an index that varies as a function of distance. So light comes in and it actually bends, and so what you see in your eye is actually the sky, and it looks like water. So that's really interesting. It says we can actually bend light, we can make it do something different, and that's exactly what we want for a cloak. So gradient index optics have been known for a while. It just turns out that they're not that easy to make, and something that negative index, or something that metamaterials we began to feel have a real natural propensity for. It's easy to do this, and so it's easy to create a gradient in either the magnetic properties or the electric properties. Very simple to do. So can we use this to make an artificial mirage? And can that artificial mirage possibly be a cloak? So maybe just to be a little, I like to look at it this way. Gradient and what I'll talk about, transformation optical materials, are the picture we're trying to create. And if you were to think of impressionistic art, metamaterials are actually the dots that compose the picture. And now we've got really a lot of colors at our disposal to make really beautiful art. So we need a tool, we need some sort of strategy to make use of all this flexibility that we have. And that tool emerged from a conversation with John Pendry, who's a very clever physicist, and suggested that we make use of a technique that he had developed years ago for numerical simulations. So I won't go through all the details of it, but conceptually it's really simple. You imagine warping space, just like I talked about at the very beginning, warping space and making light do exactly what you want it to do by actually, we call it a coordinate transformation, where you can create a ray and just imagine that light wants to travel in a straight line, change the space, and you can do what a traditional optic does. That's step one. Step two is to make use of something called invariance of Maxwell's equations under coordinate transformations. Don't need to know the details of that. Other than that, it gives us the recipe for the epsilon and mu that we need to make light do exactly this. So here's an example of a transformation. I've written down a mathematical coordinate transformation. So light travels in a straight line here. Light travels in a straight line here, but we're looking at it with a different coordinate system, so it appears to move around. So this is the coordinate transformation aspect of it. We want to make light do this, and we can do it very conceptually. Step 2 is to take that coordinate transformation, ignore all the math. What it says is that we can apply that coordinate transformation to the epsilon and mu, and immediately get the prescription for making light do that, except using a material. So it's a two-step process, and though it looks mathematical, and it is mathematical, it has a very simple application. It's very easy to do once you get the hang of it, and you can design invisibility cloaks. Here's how you do it. You imagine poking a hole in space and pushing the space away, and this can be done with a coordinate transformation from that hole. That hole is no longer part of your space, so you can hide things in there. And light, which wants to travel in a straight line, well, you can visualize what's going to happen just from this. It's going to go, and it's going to go around here like this. You just follow it through, and you can see that happens. When you poke this hole, you're actually creating a singularity, so you have to worry about what we call the boundary conditions. There's some art to that. Here's another example of how you might make a 1D cloak. You might start with some region of space and push it outward like that. You can see that this only works in one direction because just follow these lines. You can see this will take you around this cloak, but in this direction it stops dead, so it scatters this direction. This is a unidirectional cloak, works only in this direction. A couple of different ideas, but I've just shown you how to design a cloak. And even though you may not have followed it, I've also told you that because of the invariance of Maxwell's equations, I can immediately get the prescription, the recipe for making this. It's a two-step process, and it turns out to be really easy, and thanks to John Pendry for that insight, it's really remarkable. So here is a simple design for a cloak. In fact, this is the first one we did, the parameters. Turns out to be very demanding. Things can't be the same in every direction. That's called anisotropy. You have to have gradients in all the various tensors. But you can actually do a simplification if you just want to give up some of the aspects of the performance of the cloak and route the rays. So this is what we call the iconal approximation, where it's a much easier thing to achieve. It's not perfect, but it gives us some performance. So here's an example of what you could do with a perfect cloak. And now I've told you how to visualize a wave and what that looks like. So the wave comes in, and you can see that it's trying to route itself around this invisible region here and restore itself on the other side. So if you were here, you can see this looks like a plane wave, and it looks like it had passed through just free space. If we take the iconal version, which is something that we could build quickly, and I'll say why we built that quickly, you can see that there's some reflection, and I told you about that some slides ago, and there's a bit of a shadow, but actually it does tend to work, and it does tend to make things somewhat invisible, and it's a lot easier to achieve as a thing. And so this is how we do it. We take structures that look like this, and we've just gotten good at knowing which knobs to tweak in order to get the response we want, whether it's mu or epsilon. And you can see that we have actually a wide range of capability of doing that. So this is the cloak we made. This is not a negative index material, but it's a cloak, and it was made with 10 layers, concentric layers, in a ring, and we had to control mu, this parameter mu, from 0 to 0.25 and hold epsilon at other values. A very complicated material. No one's made it with any conventional material, but we can make it with an artificial material. And you can see how subtle this is. We were just gotten very good at being able to make these with pinpoint accuracy, and that's each of the layers has this unit cell that looks like that, or an element that looks like that. And it's rotationally symmetric, so each layer is the same, and we make a bunch of them, 10 steps. And this is overlaying the idea of the coordinate transformation with the material and what should happen with light. So this is what we did in 2006, measurement and simulation. And this is an artificial material. This is a hypothetical material that doesn't exist. This is what was actually made, this thing. And only if you look closely can you see the vestige of the fact that it's not a continuous material. You can see this little distortion here, but otherwise the big phase fronts do what they're supposed to do, almost identical to the simulation. And that was a great demonstrator. This is a very complex material. much more complicated, in fact, than the negative index material we did, and it worked perfectly. I didn't think it would work that well, but it did, and got a lot of attention. So it really pushed, it was very surreal to see people like Meredith Vieira and others start talking about metamaterials, something that as a grad student, believe me, I never ever thought I'd see. We made the cover of USA Today. We've been in the New York Times a few times, but this was showed, and you can actually see that they even depicted this invisibility mechanism. And this is Dave Schurig in his third interview on Fox News. And I guess he thought the sunglasses were a good idea at that time. There's actually a story to this, and he probably wouldn't want me to tell it, but I'll say it anyway, because it's a good cautionary tale. He did a couple interviews with Fox News, and he tends to blink a lot when he talks. And you don't notice it when you're talking to him, but if you look on screen, it's very noticeable. So he did something that I will never do. He went and read the chat rooms and what people were saying about him, where he had earned the nickname Mr. Blinky. So he thought these sunglasses would help with that blinking problem, but it turns out that his eyebrows were still blinking, and you could see his eyebrows going up and down behind the sunglasses. So, you know, it's just one of the things. Anyway, I like this title here, The Science of Magic. It was kind of nice. And then since then, it's really taken off. And this is a clip from the Big Bang Theory. And if you look very closely, you can see they must have a good advisor, because on this board here, they've written Vesilago's diagram that I've just shown you, and metamaterials right here, which is, again, kind of amazing. And, you know, also amazing to have been on this show with Wallace and Gromit. And just recently had a shout out from Stephen Colbert, and, you know, also mentioned on Jay Leno and lots of different places. So science fiction, science fact, you know, they kind of start to, and I like this from Dilbert. He says, I discovered a way to bend light around an object to form a cloak of invisibility. And then he says, we'll make billions selling it to the military. So it really crossed over and generated a lot of attention. And most recently, not too long ago, this the Japanese museum asked for a version of our cloak to make this diorama, and I've got no idea what any of this says, but I like the characters. And here's a picture of it here, and here's us, and this is where our cloak was supposed to be on display. And this went and toured all over Japan. And on Friday, our cloak is going to be on display. It's going to start on display at the Ray Bradbury Museum in New Mexico. So again, very close connection. Ray Bradbury is obviously a well-known author, science fiction author. So again, with all this, does it work? It definitely works. I've shown you the field patterns. That's one thing. Does it reduce what engineers care about and physicists are scattering cross-section? This is an experiment to show that it actually does work. We didn't expect it to work this well because it's not a perfect cloak. But here is the scattering, and this is all the scattering experimentally obtained from the disk that we're trying to hide, which is pretty constant. And then this is the disk with the cloak. And remember, the disk with the cloak is about 3 times larger. So normally it scatters a lot more, but right at the frequency where it's supposed to work, it plummets and actually goes lower than the thing that you're trying to hide, which is great. So you'll notice it's got a narrow bandwidth, and you can say, are we stuck with that? And the answer is yes, we're stuck with that in air. And there's a simple reason. We want to make light look like it did this. And in order to do that, we're going to make light do this. So it has to travel a longer path in the same amount of time, which means it has to go faster. So light has to go faster than light in order to be cloaked. And that can't happen. The speed of light is invariant. So that only can happen at one wavelength, one frequency, and then maybe a little bit around it, which is why all of these solutions tend to be narrowband and will be narrowband. And that's a basic fundamental reason. So, okay, that's if you can warp space-time, you can really cloak yourself from everything and change all physics at the same time. If you try to create a cloak out of material, this is your limitation. Now, if you try to cloak something in water, you have a lot better chance, because already your light is moving slower in water, because water has a high index. and so you can actually make things invisible in water with a broad bandwidth, just a nuance. Okay, one of my favorite movies, Predator. Again, there's some things that we can learn from this. If you think about what might be possible in terms of cloaking more than one color or more than one wavelength, putting power into the system actually gets you around that limitation. So our alien from the future may have solved that problem somewhere. It's not impossible. So I should check where I'm at, because this is, okay, so I won't go in through some of these other cloaks that we've done. They were a lot of fun. You can make the 1D cloak, and it reminded me of Alice in Wonderland. And that's Nathan Landy, one of the students who has recently done this cloak, which is one of the ones that I showed. He looks very happy there, and this picture just somehow made it all over the internet. So if you look around. But it's a large cloak, and what's amazing is that here is with no cloak, and you see this gigantic shadow, and you see this gigantic reflection. You put the cloak around it, you remove all that. And this is really a perfect cloak, so it actually reduces the scattering cross-section of this really large object. I'm talking with respect to wavelength, but actuality was about that big. It really reduces any scattering to about 0 as you come in from this direction. So we've actually gotten to the point where we can make very good cloaks. This was just done last year. And lots of other things. I'd like to show that, but in the interest of time, I won't. So I wanted to close with what I've talked about is science fiction, and I think we're getting closer to merging science fiction with science fact, at least in the area of invisibility. But there's a lot of other things that we're interested in, and eventually we'd like to make things useful. So somewhere along the way, somewhere around 2003 or so, this guy, who some of you may or may not recognize, Nathan Myhrvold, got interested in metamaterials. So as it turns out, he's a very accomplished chef. He's known now for having produced this 5-volume series called The Modernist Cuisine, filled with recipes that no one but him can cook. But it actually sells for about $800, and it's actually selling very well. But before doing that, he was CEO of a company called Intellectual Ventures. And before that, he was CTO of a company called Microsoft, where he did pretty well. And so we'll say he's well off. And kind of eccentric, but kind of brilliant. Metamaterials caught his attention, and he actually decided that he wanted to license all the metamaterials work that we had done at UCSD and then later Duke. So he didn't know what he was going to do with it. He just, if you hear him talk about it, he said, I just thought it was totally cool. So he brought it into this company called Intellectual Ventures that specializes in really invention and intellectual property, and began thinking what they could do with it. So along the way, say maybe 2.5 years ago, one of the students in our group, postdocs in our group, Nathan Kuntz, went to Intellectual Ventures and started on some serious marketing as to what we could do with this technology. And the result of that was a company that was spun out of Intellectual Ventures called Kymeta. The focus of Kymeta is in satellite communications. So the same things that I've been telling you about that make negative index and that make invisibility cloaks actually can do something useful. And here's just from the press release about Kymeta and the surface antenna technology that came out. This company was really funded by Bill Gates, Liberty Global, and Lux Capital, and already have a number of customers, and hopefully we'll launch products in 2014. The marketplace is a difficult place, so there's no guarantee, but they've got a good start, and we're hoping that and more will come out of it. So just to show you, when you actually think about what you could do usefully, they're targeting satellite communication. The main way of communicating with satellites, even now, is still based on 1940s technology, satellite dishes. What I showed you on like the second slide, the Jetsons with these little radar dishes on people's heads, that's what satellite communication uses. And so the idea is we can take a metamaterial, make it kind of active, and replace these is really a good idea, and possibly even a disruptive idea. and really just only one of the many, many ideas that we have for potentially commercializing this technology. This is a picture of what's being made, so you can see it's becoming much more fabrication-oriented and technological than things that we just whip up in the lab. And this is the sorts of markets that they're looking at: defense, aeronautical, rail, maritime, lots of different areas. So just recently, in fact, last week, this came out from MIT Technology Review of the 50 disruptive companies for 2013. And you can see there's Intel and Amazon and Microsoft, and you can see that Chimet has been named. So I hope that I've given you, and as briefly as I could, a little bit of starting off with science fiction and the thing that really motivates us as futurists and as scientists, and then coming back and hopefully convincing you that we're not entirely out in space, that we actually have some real thoughts of, well, to put it bluntly, how to make money with this stuff. And that needs to be a goal in addition to all the other cool stuff. So again, I thank you for the invitation. Hope you found this entertaining, and I will stop for any questions. Yeah, we have a whole effort in that, we and many others. The problem is that the materials that we base this on, the metals, tend to get lossier. So there's a lot of approaches, but now we've had some pretty good traction in making things toward the infrared. And there's other opportunities, there's other effects that you can leverage for optical metamaterials, which we're also looking at. So really, these sorts of structures actually can be scaled quite successfully to infrared if you're looking at the right application and the right design.
The name of your center includes the word plasmonic.
Yes.
What does that?
Metals have a certain response that people understand at low frequencies. It's you think of it as a conductor. Light just doesn't get in. But as you go to optical wavelengths, light does get in, and you end up with modes that exist that are very different than the response at low frequencies. So as I was just saying, there's other opportunities at optical. You can excite these types of modes called surface plasmons, which are actually coupled electromagnetic electronic modes that occur at the surfaces. And it's related to the fact that you don't have just a true conductor at optics. You have kind of the mix between a conductor and a dielectric. And so we're interested, for a long time, in fact, this started in Shelley Schultz's lab. He was also very interested in plasmonics, and it really is a very natural extension to metamaterials.
Last question, and then David will answer some more questions privately. Okay. Well, let's thank David again for